welcome to our first day of lessons. We are going to be talking about functions and relations today. So we're going to start with our definition. A relation is any relationship between two sets of information. And so there are multiple ways that we can represent a relation. We can graph them. They come in formulas. They come in numbered pairs. All of these are relations. So you can see that we have a graph of a line. This is x equals y squared. So that will be familiar to you because the y equals x squared is a parabola. This is a different kind of graph. And then, of course, we have the x squared plus y squared equals 9. We talked about that on the first day. That's the formula for a circle with radius 3. And so this may be new to you. This is a set of numbered pairs. And so that is another way that we can define a function or a relation. In this term, we're just talking about relations. So all of these things, so the equations, the graphs, the numbered pairs, these are all relations. Now, one of the things about functions and relations that we haven't addressed up to this point is notation. There's several specific notations that are very particular, and I will be very picky that you use the right notation. So if we have a set of coordinates, like you did on the previous page, note how they were surrounded by these like squiggly brackets. Okay, those brackets are also used to define and discuss domain and range, which we will be getting to. Also, when we are defining and discussing domain and range, the greater than or equal to, less than, and less than or equal to signs are very important when we talk about data ranges and data restrictions. And again, we will get to that in a bit. So this would be x can be any number greater than 2. This is x can be any number less than or equal to -5. And this gives us a range where x is going to be between -3 and 14. So there's lots of different ways that we can model relations, which we've talked about. The graph, the equation, there can be table of values, numbered sets. So we've got here an example. So we have Bob has a summer job cutting lawns for $10 an hour. The amount he earns is related to the number of hours he works. So there's many ways that we can model this relation. This is actually a function, but we'll get to that differentiation in a bit. Note, kind of like all thumbs are fingers, but not all fingers are thumbs. All functions are relations, but not all relations are functions. So I wanted to show, this is one of the ways that I'm going to suggest you make your notes to your future forgetful self, is in this type of a format where you've got what it is that we're talking about and different examples that you can also annotate to make sure that you can remember, make notes to yourself in the future. But these are all different ways to represent a function, okay? And remember, all functions are relations. So these all represent that situation we were talking about of Bob earning $10 an hour. So we have the equation of Bob earning $10 an hour. That would be pay is equal to 10 times the number of hours that he works, where P is pay and T is the number of hours worked. Here we have it as a graph. And of course, it is a direct correlation, not a partial, because if he doesn't work any hours, he doesn't make any money, right? This is new. You haven't seen this yet, this mapping diagram, but we're going to be looking at that today. The set of ordered pairs you may have seen in the past. You may not have, but this is another way to demonstrate. This is specifically for his earnings up to 5 hours, right? If he works 0 hours, he makes $0. If he works 1 hour, he makes $10. 2 hours, $20. You get it? All the way up to 5 hours, he makes $50. And here is that same thing in a table of values. So several of these you will have already seen, but note how in this mapping notation that you may not have seen before, we put the sets of numbers. So we put the X set in a bubble and we put the Y set in a bubble, and then the arrows connect the X to the Y's. So note how The reason that this is a function is because for every value of x, there is only one value of y. That's what makes a function. So we're going to get into that some more. So then it says here, what is generally the preferred way to represent a line with an equation y equals x plus 3? So I will be asking you this in class, and presumably you should be able to say to me, well, I prefer it in a table of values. Some people prefer it on a graph. Some people just prefer the equation. Any of these ways to represent, it tends to be, what is your preferred way? Probably the most common way to represent something like this would be in a graph. So here we get into the difference between a function and a relation. So you can think of the function machine where we put the x values into the function machine and we spit out, so the function machine does the work on that value, and then it spits out what's called the function of x, or the short form for this is f of x. So up to this point in your math career, we have always used y as our y equals blah, blah, blah. Well, from this point forward, very rarely will you be using y, especially in this course, because the course is called functions. And so most of what we deal with are functions, almost exclusively what we deal with are functions, apart from today. And so instead of saying y equals blah, 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 now you're going to use this f of x notation. And I need you to remember that f of x is the same as y, okay? Now, a function is a relation, like I said, where for every x value input, there is only one y value. Now, the difference in a relation is that for every value of x, there can be multiple values of y. There are a couple of ways to test if something is a function or if something is a relation. One of the ways, if we're looking at graphs, first of all, I just ask you to have a look at this, pause the video for a second, and tell me which you think of these graphs. For every x value, is there only one y value? Okay, so that's the graphic test is called the straight line test. So if you have a picture, if you can draw a straight line anywhere on the graph and only cross the graph in one place, it is a function. So note here, as soon as I get past the origin, if I draw a straight line anywhere on this graph, I'm going to hit two places on the curve. And if I draw a straight line anywhere through this circle, I'm always going to hit two places on the curve. So therefore, it is not a function. It is a relation, because there is a relationship between the x and y values, but it is not a function. Now, the algebraic test is if a relation is a function, if when you substitute any value of x, it will result in one and only one value of y. So when you look at these graphs and you say which of the following are functions, I would like you to identify quite quickly that the first and third are functions, because even though this one on the right-hand side here is squiggly, and we will get to those graphs later on in the course, you can still draw a straight line. If you drew a straight line through this, you're only ever going to hit one value, right? You're not going to cross that line more than once. So this is a function. And of course, a quadratic is a function. And this circle is a relation. When we look at something algebraically, you can immediately identify if an equation is a function by looking at the exponents if there are any. So if the exponent is on the x value, it may be a function. And so this is a line. Of course, that's a function. Y equals x cubed. If you think about it, if you put in any value of x and cube it, you're going to get a different value for y. So that is a function. Y equals 2 to the exponent x. I can make the x exponent anything that I want, but I'm still only going to get one value of y. Where you come into relations is if the exponent is on the y value. So this x equals y squared is that sort of sideways parabola that we looked at. And of course, x squared plus y squared equals 25 is a circle with radius 5. Now, if we look at a number set, remember that for it to be a function, for every value of x, there can only be one value of y. So just pause this for a second and have a look at all of the x values and then see if they repeat. And if they do repeat, are there different y values? And so for this first line, what do you think? Function or relation? And then you've got this second line. What do you think? Function or relation? So I have 1. So my x value seems to repeat. And I have a different value of y for each x value. Think about what this line, this is another line, would look like. So I've got 1, 3, 1, 4, 1, 5. Whoop, I'm not doing a very good job. 1, 6. They should be, right? That is a vertical line. Well, a vertical line is definitely not going to pass the vertical line test. Now, what about this one? This one is a horizontal line because I have 3 and 1, 4 and 1, 5 and 1, 6 and 1. Of course, I'm not doing a very good job of drawing a horizontal line, but a horizontal line will absolutely pass the vertical line test. So are all lines functions? Absolutely. Of course, with the exception of vertical lines. So any x equals number is not a function. In the slideshow in Brightspace, I have a link on the number systems. So if you go into the slideshow in Brightspace, there's a link to a wonderful, about 8-minute video on the number systems. Now, the video stops at real numbers, and we're talking about, it talks about how whole numbers are our counting numbers. So that's 1, 2, 3, 4, 5. Integers are whole numbers, but they just include the negatives. So -1, -2, +4, -7, +10. Those are all integers. A rational number is any number that can in some way or shape or form be expressed as a ratio or a fraction. And so not all numbers are rational numbers. Most of them are. A good chunk of them are. But there's a lot of them that are not as well. So that's when we get over to the irrational numbers. And the irrational numbers are numbers, they still exist, but that are things that you cannot turn into a fraction. Things like the square root of 2, right? I cannot write the square root of 2 as a fraction. I cannot write, and it's also not a whole number, and it's not an integer. So do you see how there's a relationship between the different kinds of numbers? Now, the reason that this is nested like this is because all whole numbers are in integers. All integers are in rational numbers. Now you can see we sort of have like a Venn diagram. Now the irrational numbers are not whole numbers. They aren't integers because integers are whole numbers just with a positive or a negative sign. It's not a rational number because you can't turn it into a fraction, but it does encompass the real number family. And real numbers are all rational, integer, whole number, and irrational numbers in one family group. So we will be talking most of the time about real numbers, particularly we're talking about domains and range. Now, the complex number system, I have it here just for those of you who are going to carry on to calculus. Complex numbers include the square root of -1. So they can also be sometimes known as impossible numbers, but complex numbers involve I, and I is the mathematical form for the square root of -1, which of course you're like, well, I can't take the square root of a negative number. Of course, that's why it's an impossible number or a complex number. So we only deal with those in calculus. So each different number system has its own special symbol. So natural numbers or whole numbers are n. Integers, which are positive or negative whole numbers, are z. Rational numbers, all numbers that can be written as a fraction, are q. Irrational numbers, they have here that it's r over q. It tends to not be that. The most common is actually q with a line over it. It's almost like to say not rational, right? That's what the line is supposed to mean. And then real numbers, which are all possible numbers in the world, is represented by an r. And of course, all numbers with the exception of the complex or imaginary numbers. So in class, we'll have a quick discussion about which number system would be the most appropriate for each of these measures. And because Bob could sell t-shirts for P dollars, it does say dollars, doesn't say dollars and cents. And so you could argue that the natural numbers might work for that, but that would have to presume that he is only using whole numbers and he's not charging tax, right? So he's selling them for like $10, period. You could use natural numbers for that. If we presume in the real world that there would be tax or they would be 1099 or something, you would use real numbers. Time measured in seconds, natural numbers. Measurement of object lengths. Not all objects are exactly 2 meters or 3 centimeters, so we would use real numbers. And displacements, of course, are positive or negative, and so they could be integers. They could also be real numbers. So now we're going to discuss domain and range very briefly. This will be a key part of your function unit, because when we have some inverses, we have to restrict the domain or range to ensure that the inverse is still a function, and we will get to that later on. But just so you know, domains are all possible x values for a given function or relation, and the range are all possible y values for any given function or relation. So looking at these graphs, hopefully you can get an idea of where some restrictions may come into play. The other mention is which grid is it in on the Cartesian plane. And of course the grids start in the top right corner with 1, and then it moves counterclockwise. So top left is 2, bottom left is 3, and bottom right is 4. So where on the Cartesian grid is this file, or is this line? Well, it's in 1, 2, and 3, never touches 4. Yet, all lines have, oh, I can see my range got moved over. This belongs over here. The domain for every line, unless there's a given restriction, is any real number, and the range for any line is any real number. So when you look at every time we have a line with connected points, what that's telling you is that it's not just these points on the graph. So it's not just -3, 0, -2, 1, -1, 2, and 0, 3. It's not just those dots. We've connected the dots, which means that any value here between -3 and -2 is on that line. Which is why when we have dots that are attached, you have a continuum. And so therefore, you have real numbers. So this x equals y squared graph that we've looked at before, the one that goes like this, ooh, that doesn't look very good. It is in only quadrants 1 and 4, and it has a restriction. Because as you can see, because it's only in quadrants 1 and 4, the x value is never negative. So it starts at the origin, so it includes 0. So you have to say that x is greater than or equal to 0. And there is no restriction on the y value. So that parabola, even though the y's are going to have to get very, very large before, but you could say that you could go to infinity on that parabola. It won't fit on a graph, but you could. Now this circle graph, if you look, you can see that you've got from -3 to +3 for domain, and from -3 to +3 for the range, which is x squared plus y squared equals 9 for the equation of your circle. So your restrictions, right, -3 and +3 are on the graph, so you need to include them. So it's -3 is less than or equal to x is less than or equal to 3. Always, always, always start with the smallest number. Always use less than or equal to. Never use greater than or equal to. Do not reverse these. You will lose communication marks because it is inherently incorrect. Okay, it is not mathematical form. We always start with the smallest number, and then we go less than or equal to up to the largest number. And the same with the range restrictions. We go from -3, less than or equal to y, less than or equal to 3. So it bottoms out at -3 and it tops out at +3. Now the parabola, here you can see that there is no restriction on the x value. I can have any value of x, just like over here I could have any value of y. I can have any value of x that I want. However, it never goes below -2. So my range restriction is, and because these are all connected lines, note the families, these are all real numbers, all of these. So the way you read this is you say that this is domain is, so d dot dot, and then your squiggly bracket, x is in the family, that's what this E means, of real numbers. So the range on this one, because we have a restriction, you would read this that says the range is y is in the family of real numbers, such that, that's what this little line is here. When you read that vertical line, it reads such that, and then you carry on with y is greater than or equal to -2, and then you close your bracket with your squiggly bracket. Now this one's a little harder. So we have, and remember I said that this part of the range got cut off and moved around a little bit. Sorry, that's a formatting error. So we can see this is more like an oval. So we can see that we have domain restrictions from -4 to +4. Now the range restrictions are a little tougher, so I just said that it looked like roughly 2.4. It's not quite halfway. So we go that our range is from -2.4 less than or equal to y less than or equal to +2.4. These again are slightly different graphs where we have slightly different questions being asked of us. So on this first graph, you can see that there is no restriction on the domain. Those x values can carry on in either direction wherever they want. However, you can see that the range is only between -1 and +1. Now this is a new graph that you haven't seen. And this graph is the reciprocal graph. And it has what's called an asymptote. Actually, it's two asymptotes. And an asymptote is a part of the graph or a line on the graph that the curve continues to approach but will never actually touch. And hopefully you can see that the asymptotes are here at x equals to 1 and here at y equals 2. And so what that does is it means that when you're doing your domain and range restrictions, x will never equal 1 and y will never equal 2. So it's just a different way to express it, and I'm going to do that on the next slide. This, note how we have dots on a graph. This is not a line. So therefore it's the family, the number family, is different for here. And then here we have another graph with an asymptote. Again, where is it on the grid? Well, this one is in all 4 grids. This one never touches quadrant 3. This one never touches quadrant 2 or 4. and this one never touches quadrant 2 or 3, because this graph never goes over the y-axis. So when we look at, these are a bunch of connected dots, so we're talking about the real family. So the range is, y is in the real number family such that -1 is less than or equal to y is less than or equal to 1. So it's within that very tight range between -1 and 1. And this is how you relate an asymptote for the reciprocal graph. So we have x is in the real family, because see how it can go everywhere it wants to, but it is never going to equal 1. And so that is how we say that. X is in the real family such that x does not equal 1. And y, the same thing. It can go anywhere it wants except for 2. And so we say that with y must not equal 2. So this is in the integer family because it doesn't connect the dots. It is only those points. And it is only for the range from -2 to +3. And for the domain, it only goes from -1 to +3. And so -2, 3, and -1 and 3 are on the graph. So your range is going to include those, so you're going to use the less than or equal to sign. And finally, this is an exponential graph. So we're going to get to these. And it has an asymptote. So you're going to say x can be any real number such that it's greater than 0, right? So it's not that x is not equal to 0. It's such that x is always greater than 0, because it's never going to hit that y-axis and x equals 0 on the y-axis. And there is no restriction on range. So here, write the domain and range for the following. When you're writing domain and range, remember you need to consider what number family. So this is counting numbers. And so we are in the natural number family because there are no negatives. And we can see that x is only equal to 1. So x is in the natural family such that x is equal to 1. And y only goes from 3, 4, 5, and 6. You can write this two ways. You can list them like they are here, or you can write that 3 is less than or equal to y is less than or equal to 6. You can still use that range because you have said that it is in the natural number family, so it only means 3, 4, 5, 6. Now the square root function, we cannot take the square root of a negative number. I apologize, I need to have an equal sign under here. The square root function, because we cannot take the square root of a negative number, x always has to be greater than or equal to 0. And there is no restriction on the y values. Now, this also cannot be 0 because we cannot divide anything by 0. And so therefore we have a double restriction. This is that reciprocal graph that I showed you before, the one that kind of looks like hockey sticks that goes like that. So for the parent function of the reciprocal graph, x cannot equal 0, but y can also not equal 0. So these are quadratic functions, and hopefully you remember how they move around the Cartesian plane, right? This gives me a slide to the right by 4, and this gives me movement down 3. Now this is a upward facing, right? A is positive, so it's an upward facing quadratic graph, which means that it looks like this. So you have to think that I'm going to have a lower value. It's going to have a minimum. And so I'm going to have a minimum y value. And there's going to be no restriction on the domain, because there's never any restriction on domain for a quadratic. But where I have on a quadratic is I either have a maximum or a minimum. And this is negative. And so, of course, that's going to be a maximum of the y value of the vertex. And this is going to give you the negative of the y value of the vertex. And I was kind enough to give it to you in vertex form. So we know that, like I said, there's never any restriction on the domain for a quadratic function unless something is specified. However, for just the normal function, so y equals x minus 4 squared minus 3, that means that my vertex is 4, -3. So that means that the y has a minimum of -3. And this -2 I still have a vertex of -1, +5, but because it's pointing down, I now have a maximum of y is less than or equal to +5. So based on the information given, now let's graph these different functions given these different number families. So this is all just lines, right? It's the same line, but it's what is the line in the real number family, what is the line in the integer family, and what is the line in the natural number family. And that is how they look different. Remember, the line with real numbers is connected. With integers, it's just a series of dots. And in the natural numbers, they have to be greater than 0. These functions, you have been given a specific restriction. So I've got y equals x minus 2, but -3 is less than x, right? So this means that x is always going to be less than -3, but it's not actually going to touch -3. And this second set of restrictions, I have -2 is less than or equal to x is less than or equal to 3. So it will touch -2 and 3, but only go between those two numbers. So for that first restriction, where it's a line, but we're saying it doesn't touch -3, how we denote that is, notice here we have an open dot at -3. That means that x cannot be -3, but it can be everything up to it. It just will never be -3. And because, I apologize, I forgot the equal to signs on here, because this is -2 to 3, including those numbers, they have closed dots. Now the mapping diagram always has the domain or the x values on the left-hand side and the range or the y values on the right-hand side. So you can always turn any mapping diagram into a set of ordered pairs. So the way to look at a mapping diagram and tell whether or not it is a function or a relation is to look at the lines coming out of the domain. If there is more than one line coming out of any one number, it is not a function. It is a relation, because it means that it has mapped 1 to many, right? 2 has more than one value. As soon as an x has more than one y value, it is no longer a function. Note how you can share a y value as long as for every x there is only one y value. And so this one on the left is a function because for every value of x there is only one value of y. It's not to say that they can't share or have a repeated y value. So here are the ordered pairs for these two mapping notations. And note that the x's never repeat for this first one. But see how there are twice the x has shown up. I've got 2, 1 and 2, 2. So what that means is that there is more than one y value for that x value. So it is no longer a function. Same with the double 14s down here. It means that 14 can be 4 or 6. And therefore it is not a function. So pause the video, try this one on your own, draw a mapping diagram. So you need those two bubbles like this with a domain of 1, 2, 3, 4, 5, 6 and y equals 5. So this is a horizontal line and it maps many to 1, so it is a function. Remember, many to 1 is a function, 1 to many is not. So try this one. Pause the video, try it on your own. A mapping diagram of x equals 3 and a range of 1, 2, 3, 4, 5, 6. Of course, this is a vertical line. The line is x equals 3. And the range takes you between 1 and 6. And so because it maps 1 to many, it is a relation. Your assignment for today will be to design your own example of a mapping diagram that is a function and one that is not. And then you're also going to give me an example of a graph that is a function and one that is not. And then you're going to hand this in. Homework has been posted in Brightspace, and these are your guidelines for it.